So in this second part of the thermal physics, we'll be dealing with the thermodynamic related questions. Most of the questions will be thermodynamic related, that is an heat, internal energy, and the work conditions. So now what the today's first question is. So cylinder contains of the mass, some 10 kg mass he has given of the gas at a pressure of 10 to the power of 7 Newton meter square. The quantity of the gas taken out. If the final pressure is going to be reaching 2.5 into 10 to the power of some 6, so he is asking how much quantity of the gas has been taken out in this particular process. So the initial mass is going to be the 10 kgs. So how do we relate the mass and the pressure here? From the ideal gas equation, ideal gas equation. So from this equation, we can go for the PV is equal to nRT. So that is pressure into volume is equal to gram weight by gram molecular weight into RT. So from this one, we can say that P is directly proportional to the mass. So from this relationship, we can say that is M2 by second mass by first mass. M2 by M1, or let me write this one. M2 by M1 is equal to, we can go for the pressure P2 by P1. So now we need the second mass, which is equal to the M2 by M1 is equal to, your lateral pressure is going to be the 2.5 into 10 to the power of 6 by initial pressure. He has given it to the 10 to the power of 7. So this is 10 to the power of 7. So if I can remove these things, 10 will be left over, and this initial mass is going to be given as an 10 kgs. So these two things will be cancelled. So your leftover mass finally is going to be 2.5 kgs. So from this one, but he has not asked this particular. He has asked amount of the gas taken out from the cylinder. That means initial gas minus, that is delta M, can be written as an taken out is initial mass minus final mass, which is 10 minus 2.5 kgs. That will give you the 7.5 kgs. So this is your mass that has been taken out from the system here. So that means it should be your option B. Now coming to the second question. 4 moles of an hydrogen. So N1 value or number of moles of the hydrogen given are the 4 moles. And the number of moles of the helium given as an 2 moles. And the number of moles of an water vapor, that is water vapor, is equal to 1. So these three are being mixed at the constant pressure. So he is asking the constant pressure of the specific heat and the constant pressure of the mixture is going to be how much. So he is asking Cp value is going to be how much. So this can be found out in a different ways. So first thing is going to be the Cv. Cv for the hydrogen gas, that is H2, it's a diatomic gas. So since it's a diatomic gas, it will be the pi R by 2. So Cv for helium gas is, helium is a monoatomic, it is 3R by 2. Now coming to the Cv for water vapor conditions. So this is for water vapor is equal to, this can be written as, and this is 6R by 2, which is equal to the 3R. So these are your Cv values. Now when we substitute in the Cv of a mixture, so this is an specific heat at constant volume of the mixture can be written as a N1 Cv1 plus first one N2 Cv2 plus third one N3 Cv3, that is a specific heat for the third gas, and that is equal to the N1 plus N2 plus N3. So in this, if I substitute the values, so 4 moles of first one, so it is 5R by 2, these are the standard values. This is 2 moles into 3R by 2 for the helium, and 1 mole for an water vapor. So coming to the by divided by 4 plus 2 plus 1. So this value will be coming out to be, this goes for 2 times here. This goes for 2 here, 10R plus. So 3R plus 3R by 7, which is going to be the 16R by 7. And as we know that, according to the Mayer's hypothesis, Cp is equal to Cv plus R. So if I go for 16R by 7 plus R, which will be equal to the 23R by 7. This is your first method. You can solve this question, or directly you can write for an Cp relationship, that is Cp of the mixture is equal to number of moles of the first gas and Cp of the first gas, number of moles of the second gas, Cp of the second gas, plus number of moles of the third gas, Cp of the third gas, by total number of the moles of the mixture, that is N1 plus N2 plus N3. So since our first gas is an hydrogen, 4 moles are there. Hydrogen gas is a Cp value is going to be there. You can write it as an 7R by 2 plus. So number of moles for the helium 2 into it is 5R by 2 plus this one is going to be the 4R whole divided by all of them will be equal to 7. So this goes for 2 times, this 2 can cancel. So that will be the 14R plus 5R plus 4R by 7, and which results in a 23R by 7. So in either method, you can go for solving this particular sum. So whatever values you can remember, that will be the 23R by 7. So next case, a gas under the constant pressure, that is 4.5 into 10 to the power of 5 pascals, is subjected to the 800 kilojoules of the heat. So pressure here, they are given pressure is equal to 4.5 into 10 to the power of 5 pascals, and it is subjected to an heat, that is Q is equal to, or dq can be written as, and this is 800 kilojoules, or we can write it as an 800 into 10 to the power of 3 joules. And the volume is changing from, that means V1 value we can write it as an 0.5 meter cube, and V2 value can be written as an, it is 2.0, this is meter cube. Now he is asking the change in internal energy is going to be how much. So according to the first law of thermodynamics, that is dq can be written as, and it is du plus this is dw. From this one, the change in internal energy du or delta u can be written as a change in the heat minus work done, delta w. So in this one, delta q has been given. We have to go for a delta w, or the change of work done can be written as a pressure into delta V, or which is P into, this will be the V2 minus V1, final volume minus initial volume. What is the pressure given? 4.5 into 10 to the power of minus 5, and this is 2 and 0.5. So this is 4.5 into 10 to the power of 5, and the volume V2 can be written as an 2 minus, so this will be the 0.5. So given it as a 2, and this is 0.5. So this will be equal to the 4.5 into 10 to the power of 5 into this will be the 1.5. So now when we multiply this one 15 into 45 and all these things, this will be equal to the 6.75 into 10 to the power of 5 joules. This is your work done. Okay, so this is your work done condition. So next one. So since we have got the work done, we can substitute in the first relationship, that is du can be written as an, or change in the internal energy is equal to the change in the heat supplied or heat supplied into dw. What is the amount of the heat supplied is 800 kilojoules, which is 800 into 10 to the power of 3. Let's write it also into 10 to the power of 3, also 375 into 10 to the power of 3. So 800 minus this will be 675. That will be the 125 into 10 to the power of 3 joules or kilojoules. Try to convert that into the given format. D is your option, that is 1.25 into 10 to the power of 5 joules. In this format, he has given in the question, that is your D. So next one, sir. An insulated to 0.2 meter cube. So he has given the volume. So it's an insulated one. Volume is equal to 0.2 meter cube volume he has given. So next case, the tank contains the helium at some pressure he has given, that is 1200 kilopascals pressure he has given, and temperature 47 degrees centigrade. The valve is now open, allowing the helium to escape. So some helium has been escaping from here. The valve is closed when the half of the initial mass has been escaped. So then how do we go for this one? So volume we have given. Let me take the values initial mass to be the m. Now you are allowing it to the half of the initial mass. That means the final mass is going to be the m by 2. This is the first and primary information that we have got. So now temperature he has given it as an T1 is equal to, or in terms of degrees centigrade, this is 47 degrees centigrade. In terms of the Kelvin, T1 can be written as an 47 plus 273, and that comes out to be the 320 Kelvin. So on the initial pressure he has given, that is P1 is equal to 1200 kilopascals per kilo 10 per 3. This is pascals, or we can adjust it as an 1.2 into 10 to the power of 6 pascals. Okay, so we are going for the order of the merit. So next one, this is the condition. These are the information we have written. Since it's an insulated one, the change in the heat, this is dQ is equal to 0. That means it is an adiabatic process. Adiabatic process. Fine, sir. So since it's an adiabatic process, conditions dq is equal to 0. And now from first law of thermodynamics, so dq is equal to du plus dw. This is equal to 0, which implies your du will be equal to the minus of dw. This is a primary relation. Now let's try to get the relationship between the mass and the this changes in the pressures and all these things. So now from ideal gas equation, we can write that when PV is equal to gram weight by gram molecular weight into RT. So this is in the case of an ideal gas, since it is dq is equal to 0. So dq means why dq is equal to 0, since it's an isolated chamber. So isolated in the sense, isolated means no heat is been going from the system or no heat is entering to the system. So due to that, change in the heat will become 0. Since change in the heat is 0, from first law of thermodynamics, dq is equal to du plus dw. So since dq is equal to 0, this is the relation. Now from the ideal gas equation, PV is equal to number of moles can be written in this format, and the mass can be written as n. Since it's a given gas, or from this relation, you can go for the mass is equal to, it is PV into molecular weight by RT. In this particular function, in this relationship, so mass is going to be, this is the V, that is volume, M molecular weight, Molecular weight are all of them are nothing but constants. So mass is going to be dependent upon only two factors. So m is proportional to the p by t. So from this relationship, you can say that since mass is becoming half, so I'll go for like this. So m1 by m2 or m2 by m1 is equal to m2 value is m by 2, initial mass is m. This information he has given in the question itself. Next, and that should be equal to the pressure. We can write it as n. This is going to be the P2 by P1 into this will be the T1 by T2 relationship. So since if I can remove this one, so 1 by 2 is equal to pressure P2 by P1 into temperature T1 by T2 relationship. Or from here you can say that P2 by P1 is equal to the 2 times of pressure P2 by P1, or you can write it in an inverse case. According to the situation, we can alter this one. So keep it aside. Next, since it's an adiabatic process, since it's an isolated system and dq is equal to 0, so adiabatic process. So relation between the pressure and the temperature can be determined as n. So this is the T is or T to the power of gamma into P to the power of 1 minus gamma should be equal to the constant, or from this relationship I'll write the T1 by T2 or T2 by T1 is equal to this is equal to the P2 by P1 whole to the power of this will be actually 1 gamma minus 1 by gamma. And what sort of a gas it is? It's an helium gas. So since it's an helium gas and it's an monoatomic, so since it's a monoatomic gas and the gamma value for the monoatomic gas is going to be the 5 by 3. So when you substitute this 5 by 3 value in the given relationship, so pressure we will be having the relationship between the pressure that is P2 by P1 is equal to 5 by 3 minus 1, that will be the 2 by 3 by 5 by 3. So this comes out to be the 2 by 5. So now if I reverse this case, or pressure P2 by P1 is equal to, so this can be written as an T1 by T2 whole to the power of 5 by 2. Since we do have some sort of a relation between us, that is P2 by P1 here can be replaced with T2 by T1, or this value you can put it over here. So if I substitute on, if I reverse this particular case, so I can write this one as an this is T2 by T1. In the sense, I'll be replacing this one with the reverse case, that is T2 by T1 to the power of. This will be the 2 by 5. And just replace these two things here, sir. So P2 by P1 can be replaced with this is 2 times of or 1 by 2 times of. This is 1 by 2 times of P2 by P1 can be replaced here. That is T2 by T1. Now take them to the one sides, please. This is whole to the power of 1 here. So take it to the other side. So that becomes as an T2 by T1 whole to the power of this is 2 by 3 is equal to, this will be equal to the 2. When it comes to this side, it will be the or negative sign. This will be the 1 by 2 or 2 to the power of minus 1. That can be removed here. So from this relation, you can say that T2 is equal to, so T1 to the power T1 by 2 to the power of, it will be coming out as an 2 by 3. So square is there to the power of 1 by 3 is there. So I'll just continue here. So from this one, T2 can be written as an initial temperature is 320 by this can be written as an cube root of cube root of 4. So what is the value of the cube root of 4 given in the question? That is 1.6. So that will be equal to the 320 by divided by 1.6. 62s are 32, so it should be the 200 Kelvin in this case. 200 Kelvin, if you want to convert it into the degree centigrade, T is equal to. So we can go for it as a 200 minus, this is 273, and that will be the minus 73 degrees centigrade. So since it's a multiple answer question, you can go for the 200 Kelvin and minus 73 degrees centigrade. So both of them will be, work it out please. This can be worked out. So next one, sir. In this case, so it's a quasi-static process system undergoes the three quasi-static processes sequentially indicated in the figure 1 to 2 in an isobaric process 2 to 3. So this process, first process is isobaric process. Isobaric in the sense pressure is constant here. And the next process 2 to 3. 2 to 3 is a polytropic process. So it's a polytropic. Next one with the gamma value also he has provided to us. 3 to 1 is an PV is equal to constant in the sense it should be an isotherm. So it's an isothermal process. So these are your three processes given here. P1, P2, all these values are being given here. So he is asking to find out the heat transfer to the cycle. So since it's a cyclic process, since it is cyclic process, du should be equal to the, or delta u should be equal to the 0. That means this should be your first option. Now coming to the other case, since dq is equal to 0, du is equal to 0. Now from first law of thermodynamics, delta q is equal to delta u plus delta w. Since internal change in internal energy is equal to 0, delta q is equal to change in the work done. So now what are the work done here? Delta W is three types of the work done, that is work done along the first to second process, plus work done from second to third process, plus work done from third to first process. It's a cyclic one. So what we have written, sir, in this phase, so work done from first to second process is an isobaric process. So what is the work done relationship under the isobaric process? Pressure is constant, volume we have to go. So what is the volume? This is 1 and this is 2. So pressure is constant over here. So P1 and P2 are the same values. So P1 into this can be written as an V2 minus V1. So this is your first one. What is your P1 value and into the V2 minus V1? Let me substitute here. P1 is equal to 4 into 10 to the power of 5. And the volume which is been V1 and V2. So V1 he has given, we don't have the V2. Okay, so I'll just write down in this information here. This is 4 into 10 to the power of 5. We don't have the V2, but V1 is equal to 1 meter cube he has given. We don't have the V2 value. Okay, so that is the first problem, first issue. So now coming to the second part of this one, so I'll be substituting here. So V2 minus 1. So we'll be solving it later. Next one. So second case, work done under the 2 to 3. 2 to 3 is a polytropic process. Work done under the polytropic process is 1 by, this is 1 minus gamma into. So pressure relations P3, V3, actually it should be T3 minus T2. So I'm going for the NRT, I'm taking into that one. I'm writing in this particular format. So these are your information set. So for this case, do we have the values of the P3 and P3 value? We do have P1, P2 value, we do have V3 also we don't have. So and V3 is unknown. So these are the two important values that we need to find it over here. So if I substitute the values, this will be the 1 by what is the gamma value is 4 by 3. That is values that we don't know here. So P3 is how much, sir? P3 is so 1 into 10 to the power of 5, and this is 4 into 10 to the power of 5. So this is 1 into 10 to the power of 5 into volume V2 or V3 minus 4 into 10 to the power of 5 into volume V1 whole divided by 1 minus 4 by 3. So in this one, two unknown values are there. Those are V2 and V3s. So there is another work done. So work done, that's an isothermal process. So work done from 3 to 1, last process is an isothermal. According to the isothermal formula will be the Nr into the temperature at that particular instant is going to be the T3 maintaining its same into this will be the Ln of this will be the final value of volume by initial volume. Sorry, V1 by final volume by V3. This is our relationship. Okay, so these are your formulas for the given situation. So we need to substitute them. So here, if you can find out the V1 and V2, we can go ahead for solving the questions. So since 3 to 1, PV is equal to constant, that's an isothermal condition. We can write it as a P3 V3 is equal to P1 V1. And we know that, so I'm just holding this one here. So let me try to find out these values in this section. So from this one, V3 value, we don't know P3 is. So what is the P3 value is 1 into 10 to the power of 5 into V3 is equal to pressure P1. P1 and P2 are same. 4 into 10 to the power of 5 into 1. So that means V3 value will be equal to the 4 meter cube. So one of the value we have got out of the two unknowns, another value is we need to find it is V2. So from 2 to 3 process. So 2 to 3 is a polytropic process. So under the polytropic process, what is our relation? That is P2 V2 to the power of gamma should be equal to the P3 V3 to the power of gamma. So as we know the value of the pressure P1 and P2 are same. So what is the value of the P1 is the same thing and P2 is also same 4 into 10 to the power of 5 into volume V2. V2 is the unknown value V2 to the power of gamma is equal to P3. 1 into 10 to the power of 5 V3 value we have got 4 into the power of gamma. So if I remove these two things and so V2 value we need actually. So if I go for that particular relationship, so I'll be getting it as a V2 is equal to 4 into this is 1 by 4 whole to the power of gamma that is 3 by 4. So that means it is cubical 4 cube by 1/4 of this particular thing. So V2 value you'll be getting it as an root 2, sir. Or else you can solve this one 4 to the power of 1. This when I take it to the numerator 4 to the power of minus this one. So overall leftover is going to be the 4 to the power of 1 by 4. 4 to the power of 1 by 4 can be written as an 4 to the power of 1 by 4 can be written as an 2 square into 1 by 4. So that comes out to be this is 2. That means so final value will be equal to our root 2. I'm erasing this particular. So now we have got the V2 in this section. Let's go for the volumes or the work done in every space. So now work done in the first stage, first to second stage is 10 to the power of 5 times of root 2 minus 1. Now here, so this will be the 3 minus 1 will be here. So that will be equal to the, so 3 will be going to the numerator. So we can solve this one and I'll write it and this one. V3 is going to be the 4 and V2 is equal to root 2 term is there. So now on substituting overallly, we can get it as, and this is 12 into root 2 minus 1 into 10 to the power of 5 term will also be there. Now coming to your last work done, that is an isothermal process in this case. So nRT, this can be written as, and this is P3V3. So or else P1 V1 also the temperature is going to be the same conditions. So this can also be replaced with the 1 at the first relation. So if I go for the P1 V1 relationships, P1 and V1 into, so what is your first volume is 1. So into, this is ln of, we'll be writing it as an volume V1 by V3 1 by 4 like this. So it's been volume has been decreasing. It's a negative sign will be there. If I take that inside, it will be the completely. So let's calculate this one. So PV is equal to, this is 4 into 10 to the power of 5 and ln of the 4. Log base E, that is your 4 value, can be written as, and it is, and multiplying with 1 per 2.303 base 10. So 1.386 it should be the case. Now substitute in the Q, as we know that delta Q is equal to change in the work done, which is equal to the work done of all these things. So substituting all these values, 4 into 10 to the power of 5 into, this is root 2 minus 1, and the second term is 12 into 10 to the power of 5 into, this is again root 2 minus 1, and the next term, last one, that is equal to, this will be the negative, since it's here the work done is negative for the, because volume is decreasing. So this can be written as a 4 into 10 to the power of 5 into, this is 1.386. So this is our relationship. So on substituting an addition of the 12 plus this 16, it will come down, and subtracting from that one, this will be the 1.08 into 10 to the power of 5 joules. Just go through the concept, that's a very important. So this is also true. So these two things are the true. So your answers will be the B and C, multiple answer question. So coming to the next part of this one, this is two identical vessels are there. A and B are connected by a wall. So two identical vessels in the sense both should be look like same. That means their volumes should also be same. Since they are connected by a pipe, their volumes are same. So that means I can write it as an V1 is equal to V2 is equal to V. This is our primary thing. So volumes are same and they are connected on the other side. So when they have been connected, what can you have the maximum pressure difference? Not less than this one. So this is the pressure that needs to be maintained at that particular instant. So now, initially, before connecting them, the pressure of the first one is 1 into 10 to the power of 5. And the container B 1.5 into 10 to the power of 5. The two vessels are at the temperature. So temperature is also same here. Temperature T1 is equal to T2 is equal. That is 300 Kelvin. This is constant. So two vessels are maintained at the same temperature. So now from ideal gas equation, so in this case, what is your ideal gas equation? Just I'm writing in abbreviated form. In the next time, if I write it as an IGE, it represents the same thing. So that means PV is equal to, that is nRT. From this one, volume can be related, V is equal to nRT by pressure. So in this case, since V1 is equal to V2, so this will be written as a number of moles into R, N1 into R into temperature is constant. Pressure of the first one is equal to number of moles into R into temperature is constant by P2. So if I remove these two things, so what is the question he has asked? Ratio of the number of moles of this one. So that means we can N1 by N2, A to B or B to A to B only he has asked. N1 by N2 is equal to. This can be written as an pressure P1 by P2. So what's your pressure in the first case is 1 into 10 to the power of 5. Another one is 1.5 into 10 to the power of 5. So 1 into 10 to the power of 5 by, I'm writing 1.5 as 3 by 2 into 10 to the power of 5. So remove this one. So they should be in the ratio of 2 is to 3. So this is the value of the ratio of the N1 and N2. So that is your option B. So this is the one he has asked. Okay. Seventh question, two identical. Okay, it's a paragraph question. First question is in the sixth question. Seventh question is an continued question. What is this question? Every values are the same. Which of the following statements are true? He is asking about the fractional increase or decrease in the number of sorry, number of molecules of the two vessels he is asking. So that is number of moles. Small n is proportional to the number of molecules. So in that particular sense, if we go for this one. So as we know that P1 by P2 is equal to N1 by N2. This is the relation that we have obtained in this case. It's the same question, continuation question. The same relation I'm using here again. So now this should be the initial pressure P1 and this should be the final pressure of that situation. So then I'll write this one as an final pressure P and this one is N1 dash. So when I substitute 1 into 10 to the power of 5, what below which the final pressure has to be definitely 0.25 into 10 to the power of 5. So substitute that one 0.25 into 10 to the power of 5 is equal to. So initial number of the moles N1 by N1 dash. These two things will go off here. So 0.25 can be written as an 1 by 4. That is 1 by 1 by 4 is equal to N1 by N1 dash. Or from this one, N1 dash is equal to 1 by 4 times of N1. So this is the value of the final number of moles in the container A. So let's see the option here, please. So the fraction of the molecules, this is 12, this is B, this is A. Okay, it's not 1 by 4, so this is again B, this is A. So your option D has to be the correct option. So next one, sir. A vessel contains 1 mole of an oxygen water at a temperature T, and an identical vessel contains of the helium 1 mole of a helium gas. It's a diatomic gas and it's a monoatomic gas. Temperature is 2T. Find the ratio of the pressures. So it's a direct sum. You can go for this case. So initial pressure, let me take P1 is equal to P, and the volumes are vessel contained. So same identical vessel. That means V1 is equal to V2 is equal to V. So temperature of the first gas is T and the temperature of the second gas is 2T. He is asking the another pressure. So from ideal gas equation directly you can solve this one. Ideal gas equation pressure is directly proportional to the temperature here since volume is constant. So we can go for the P2 by P1 is equal to temperature T2 by T1. So from this one P2 by initial pressure is P, which is equal to the temperature 2T by T. So this can be removed. So P2 is equal to 2 times of the initial pressure. Or if we are asking the ratio, that is P2 by P is equal to 2. So that should be your answer. Sir, it's a numerical based question or integrate if you can take it as a. So next one, sir. So next case, please. Question number 9. A vessel contains an helium which expands at constant pressure when 15 kilojoules of the heat is being supplied. The variation of internal energy of the gas is asking. So it's an heat is when at constant pressure is there, heat is being supplied to the system. He is asking the variation of the internal pressure. So that means from first law of thermodynamics, we can write it as an dq is equal to du plus dw. So from this relationship, dq can be written as an ncp dt and du can be written as an ncv dt. So since he is asking the internal energy, we do have only one value dq. So I'm just going for du by dq can be written as an it is Cv by Cp, or this can be written as an 1 by gamma. Since helium is an monoatomic monoatomic gas, so what is the value of this monoatomic gas is gamma is equal to, it is 5 by 3. So when I substitute over here, this will be the 3 by 5. So it will be divided in ratio 3 parts of the du and 5 parts of this one. So if I want the du, it will be the 3 by 5 times of the dq. So from this one, 3 by 5 times of the dq is given as an 15 kilojoules, 15 into 10 to the power of 3. This goes for 3 times. It is 9 kilojoules. Next one, sir. Match the change in the internal energy of the system in the given column to the situation. So first one, heat is absorbed 500 calories and of heat, and at the same time it does 400 joules of the work. So if I go for the first question given, so dq is equal to, he has given it as an 500 calories of the this one. So 500 calories converted into the joules, 500 into this is 4.2. What is the value of the 500 into 4.2 is going to be 2100 joules. And given that work done is equal to, it is 400 joules. So it's a direct relation, du or delta u is equal to the dq minus delta w, first law of thermodynamics. So 2100 minus this is 400, that comes out to be the 1700 joules. So this is a relationship. So that means first should be related to the B. So one related to the B is only in the first option. Or if I go for the remaining also, heat absorbed is going to be the 300 calories for the second question. That is delta Q is equal to, it is again 300 calories he has given. Convert the 300 calories into 300 into, we can multiply with the 4.2. So then what the value it should be? 1260 joules. This is the heat supply. Next one. Work is at the same time 420 joules of the work is done on it. So work is done on the system is negative. So that means delta W should be equal to the minus 420 joules. So that means delta U is equal to delta Q minus of minus delta W. So which will be written as an 1260 plus 420. And that comes out to be the value of 1680 joules. And the last case, third case in this one, where the heat is being 1200 calories of the heat is removed from the system. Removing means you are taking from the system, so it should be the negative 1200 into this will be the 4.2. So 1200 into 4.2 should be equal to the minus 5040 roughly. This will be the joules. And next in the same question, sorry, in this case, and the constant volume. So that means since V is equal to constant, work done has to be 0. Since work done is equal to 0, delta Q is equal to delta U. So that comes under the value of, this is minus of 5040 joules. So that means it should be related to your the first one nearly, and this is related to here. The answer is going to be your first option.